Hello, here we have a circuit diagram with a single battery and 4 known resistances and 3 questions, A through C. I'm going to answer those questions by analyzing the circuit. And I'm going to start by redrawing it with some equivalent resistances shown. And I'll do that over here. There's the battery. Here's the resistor in the top branch. That, of course, is 14 ohms. Here's the resistor in the bottom branch. And that, of course, is 7 ohms. There we go. Okay, and then my 40-volt battery. Now, to answer these questions on the left, I don't actually have to ever combine these two resistors, the 14 and the 7, using parallel resistance combination formulas. And the reason I don't have to bother to do that is because I know that the potential difference across each of them is 40 volts. So with that information, I can just go right ahead and determine the current in each branch of this circuit. And to do that, I'm just going to use Ohm's law. So the current will be the potential difference across each resistor divided by the resistance of that particular resistor. So applying that logic here in this top branch of the circuit, again, there's 40 volts of potential difference or a voltage drop across the 14 ohm resistor. So we would just take the 40 volts and divide it by the 14 ohms. And that's our current, 40/14ths of an amp. And we'll label that, I suppose, as I1. Okay. And then in here, in the lower branch of the circuit, by the same reasoning, we'll call that I2. And I'm going to wind up with a current there of 40 volts divided by 7 ohms. And while we're at it, I suppose it would just be instructive to talk about the total current, IT, down here. Since there is a junction at that point right there, also referred to as a node, there's also one over here. By the law of conservation of charge, the current that goes into the junction must equal the total current that goes out. So charge can't be created or destroyed at that point. That means that this total current has to be the sum of the two that leave the junction. So in other words, it's just a fancy way of saying that the total current is equal to 40/14ths plus 40/7ths, which is 120 over 14 amps. And I think that works out to be, let me see, 120 over 14 is 8 and change, 8.57. So 8.57 amps is the total current in the circuit. All right, but the problem doesn't ask that. The question in part A over here is to determine the total power output of all the resistors in the circuit. And I'm going to answer that question by using the law of conservation of energy, and also assuming that the wires themselves have no resistance and the battery doesn't have any internal resistance. And therefore, I know that the energy that's input to the entire circuit by the battery must equal the energy that's output by all of the resistors together. And that's certainly true in any span of time. So to calculate the total power output of all the resistors, all I really need to do is calculate the total power input from the battery. And that'll save me a little bit of time. So to do that, I'm going to use the standard formula for power, P equals IV, like that. Okay, and I'm just going to come over here and look at the battery when I do that. And I know now the current through that battery is 120 over 14 or 8.57, and the voltage is 40. And so all I have to do is multiply those two numbers by each other, and I will come out with 120 divided by 14 times 40. 343 watts. That is the input power, which, of course, as I said, must equal the sum of all the outputs from all the resistors. Maybe that makes it clear. Okay, now if you wanted to go through and actually check to see if that's valid, you certainly could do that. And if you did, you probably would want to use a different formula to calculate the power dissipated in each resistor, because right now I don't technically know the voltage drops across the different resistors. I mean, coming back to the original diagram, I know that the voltage drop across those two is 40, and similarly for the two in the bottom branch, but I don't know the individual voltage drops across each one. I realize they have to sum to 40, sorry, I misspoke, to 40, but they're not equal. In other words, it's not like you have a 20 volt drop here and a 20 volt drop here, because those are different resistances, so you would expect to have the larger voltage drop across the larger resistor. And I could certainly go through the process of finding the voltage drop across each one of these resistors if I wanted to, because I know the current through the top branch, and I know the current through the bottom branch. But in the interest of saving some time, instead of doing that, I can just as well calculate the power for any resistor using the formula P equals I squared R. That's just as good. And then I don't have to bother finding the voltages. So if I were to do that, then to find the power for the top left resistor, I'd just take the 40 over 14, and I would square that, and I would multiply that by 6. Then I would do the same thing for the next resistor, 40 over 14, and I would square that, and I would multiply that by 8. And actually then what I want to do at that point is come in here and put a plus sign in between these two. Okay, and then I would come down and do the exact same thing with the two resistors on the bottom, using the appropriate currents and resistances. And when I was all done, I'd have 4 power terms. Those are the power terms for the dissipated power in each resistor. And if I added all of those up, and I'm not going to bother to do it because I promise it works out, if I add them all up, I'm going to wind up coming out with 343. Again, provided that there's no internal resistance in the wires or in the battery, or any resistance inherent in the wires. Okay, so that's a quick way to answer the question. 343 watts. Great. Moving on to part B. If I want the total energy that's been provided by the battery in 10 minutes, if you recall that power is just simply work, the rate of doing work with time, like so, then we can say that W is the integral of power with respect to time, like so, dt. But in this case, the power is constant. It's not a function of time, so I don't actually have to worry about integrating. This just kind of collapses to multiplication. And when it's all over, I'm basically just saying that 343 watts, which is a watt is a joule per second, so 343 joules per second times 10 minutes, which is 600 seconds, gives me the total number of joules that the battery has delivered to those resistors throughout that 10-minute period. And so just calculating that quickly, 343 times 600 is 205,800. 205,800 total joules of energy in that period of time. Okay, essentially what I'm just doing there is I'm just saying that the total energy, which I'm technically calling it W in this context for work, is equal to the power times the time, because I can forego the integral. The integral would be necessary if I had some situation where I had like power as a function of time instead of just being 343. If it was something like, I don't know, 5t, some such thing, then I would actually have to do the integral to determine from some, from t equals 0 to t equals, what were we, 600 in this case. I'd have to perform the integral for real to get the total number of joules. All right, but that's our answer for this case. And then lastly, for part C, this old saying that certainly I've heard, I don't know if you've heard it, but I've heard many people say this: electricity always takes the path of least resistance. Is that true? Can it be made better? What's the deal with that? I have a couple of problems with it. My first one is that I don't know that it's really quite clear what anybody means by the word electricity, just by itself. What are we referring to when we use that term? Do we mean voltage? Do we mean power, wattage? Do we mean current? And so that word all by itself, the term electricity, is kind of sort of a nebulous concept. It's not really clear to me what it means. In physics, we certainly have better words that we can use to describe this larger phenomenon called electricity. But I think most people would say that this word right here is referring to current, right? I think that's what we mean when we say electricity takes the path of least resistance. The current, the actual charges themselves, the flowing of electrons, the moving charges follow the path of least resistance. And while in this diagram up here, I'm certainly not talking about electron flow because I'm using conventional current models. I think for our purposes it's sufficient. So is it true that current always takes the path of least resistance? Certainly not exactly, right? Because in the diagram you can see that there were two paths at this node point right here, and the current didn't just take the path of least resistance. It took both paths, right? Some of it went on the top through the top branch, some of it went through the bottom branch. So I think it's inappropriate to say this. Electricity doesn't always take the path of least resistance. What's true is current takes all paths. More of it will take the path with the lower resistance, but certainly it will follow all paths. And I think this is an important concept. Electricity doesn't just, or current doesn't just go one way. It goes all ways. But more of it follows the route that offers less resistance. And that you can see that borne out right here in these numbers. The path with the 7 ohms has a larger current than the path with the 14 ohms. Okay, I think that wraps this up. Thanks for watching.